Okay, so here we are in SolidWorks. We've got a model that I've created that I want to run today. Um, so the first step to actually creating a star sim is creating a model that you can use in that star sim. We can't actually use SolidWorks files directly, so we want to use a different format that Star can understand. To do that, we're going to go ahead and save this file that you've created, or save this model that you've created. Save as. You want to go down and save as an IGS file. This is the format that we use. We've used for all these sims. Seems to work fine. Maybe there's something that Star can interpret better, but we haven't had too much issue using this. So go ahead and save this as save this as an IGS file. I've actually already got it saved in here, but you just go ahead, click save, create your IGS file. So, wherever you want to save that on your computer, and then that'll be good to run. We can go over to Star here. Get rid of this. But once you open Star, you get this nice blank screen with nothing in it, and you want to go ahead and start making your sim now that we've got that file created. So go click File up here in the corner, New, and you've got a few options here. First off, you've got your process options, and this refers to the number of processes that Star opens with the simulation that you create. And generally you want that number to kind of relate to the number of cores or number of threads you have on your computer. Cores, physical cores, and threads, they're generally speaking 2 threads per core. On a given CPU, you may not have that. You may just have 1 thread per core. But you can look that up for your specific computer. You can find out on the internet information about that. And generally speaking, I input the number of physical cores that I have here. For the setup process, I find that runs faster with the volume mesh that we're going to create. That's the main multi-threaded process that we have. And then later on the line, I'll up that based on the number of threads. I usually run on 28 to 30 threads on this computer. I've got 16 physical cores and 32 threads. And so I will leave a few open just in case I want to do something while this runs, because it does take a while. But try to maximize that overall efficiency later on the line with more threads being leveraged. But here, I'm not entirely sure why, but this seems to be faster, so I generally use the number of physical cores. And then, if you're opening this for the first time, these 2 boxes will be unchecked. You want to go ahead and check power on demand here, because that'll connect you to the license server that we use to access Star. We've got the license key here, and we can give that to you if you want to run stuff. We have that. But yeah, once we've got this all set up, we want to click OK. It'll take a minute here, but it'll create the simulation for us. Create kind of the base for that simulation. And yeah, there we go. We've got not a whole lot populated here, but we're going to go ahead and add a lot of information to these fields to create the simulation. So the next step, obviously, is to import that IGS file that we've created. To do this, I just go here, boom, file, import. I always import a surface mesh. I think technically you could import a volume mesh, one of the options below there, but it seems to work. Have no issues doing that. So I just go ahead and import a surface mesh. You can see the model that we're going to run here. This is what we just created in SolidWorks, or created from our SolidWorks file. So I'm going to go ahead and click on that, click open. We don't change anything here. This seems to work pretty well. And there we go. We've got a model imported into our simulation here. And then the next step in this process is to go ahead and we're going to create a box. And what this box does is this kind of defines the overall region of airflow that we're gonna simulate here. Obviously, you can't simulate an infinite amount of air. That would it's computationally impossible. So we set a box, a region that we want to simulate in, kind of just like a wind tunnel. I tend to think of it in that way. It's pretty similar, just a virtual version. And so there are a number of ways to go about doing this. You can make the box in CAD with the part, or with the body, the model that you want to import. It'll just come with it, and you can create your wind tunnel that way. You can create the box within the CAD engine within Star here. That's the method we tend to use for our more complex sims, where we want to get a nice, we want to really refine that box size. We want to know exactly how big it is. The method I'm going to do here, this is what I do for all my, simpler sims, for Wings and Freestream, or for, a more simple two-body simulation like I'm doing here. This method, to me, seems to be the easiest. But it does have one flaw that you'll see here in a little bit. But what I'm going to do is I'm going to go up to parts here, and right click on that, go down to new shape part here, and then click on block. Boom. And as you can see, it kind of creates a block that just wraps the model that you've already imported. This is too small for the tunnel that we want. So we're going to go ahead and increase the size of this up here. You can also do it by dragging these in and out, but I kind of like having a little bit more precision by changing the size, just with numbers. And we're going to go ahead. I have a couple of these values already figured out, but I'm going to just set them and walk you through here. So I picked 3 meters for in front of the body here. That just gives some space to make sure that the flow is nice and clean in front of the body, and that if it does create disturbances out in front of itself, that those don't propagate into the inlet and cause issues that way. Generally speaking, we know this body is about 3 meters long. The wing is 1 meter. The car's about 2 meters, or this area is about 2 meters. And so generally I use, rule of thumb is 1 to 2 times the body length in front of the car, just to make sure you get that nice clean flow. And then we're going to go ahead and set this behind it to 15 meters. And that's you want definitely more space behind the vehicle. It's going to throw a pretty big wake behind the body, especially these high downforce wings throw a really long wake, and we want to be able to see that and kind of understand the effects of that long wake a little bit better. So I go 15 meters on this specific sim. General rule of thumb is, maybe 4 to 6 times the reference length of your body. So this is 5 times, about 3 meters. Obviously this whole box creation isn't supremely precise. Obviously there's some bits that do need to be precise. You want your ground to be in the right place, but it tends to relate to how much computational intensity you're willing to handle, how much accuracy you want in the sim. So yeah, if you make your box bigger, you're going to get more accurate, but it's going to take longer to run. So that's a trade-off there. For this, I'm going to set it to 0. I want to be able to simulate the ground with this bottom plane, and that gives us a nice, decent gap there to represent the ride height of the car. In this, I'm going to go ahead and set 5. This is a little more ambiguous, per se, that top plane. But these, this wing is going to throw a pretty high wake. You definitely want some room to be able to understand that and see what's going on there. And then for this, I'll scroll over here. I'm going to set the width to negative 2.5. Again, this is kind of up to your discretion, and depending on the level of accuracy you want in your sim, you'll go wider, you'll go narrower. But these wings, they tend to throw pretty large vortices in this direction here, and we want to just be able to see that. And this seems to create a box that's just you know, it's right within the computational range that I'm looking for. But yeah, you can play around with these numbers. They're definitely going to be relative to whatever you're trying to simulate. But these are, yeah, some good frame of reference that I tend to use. We're going to go ahead and click create here. It's not going to exit out of this window, but that's fine. You just click close. As you can see, that box disappears. And this is the one kind of problem with this is, or creating the box in this method, is that you can't see it once it's finished. So it's, if you made a mistake or some dimension is off, that can be a little bit painful to troubleshoot. You can obviously go in here and click edit part and scene, and then you can go in and change stuff. But yeah, that is the one downfall. So next, I'm gonna go ahead and actually, you can see here. Yeah, I'm gonna split all these surfaces. As you can see, Star kind of treats this block as one big surface, and we don't want that. We actually want to be able to set different properties for the different surfaces, based on how they're going to interact with the sim. So we're going to go in and we're going to change this. We're going to, go through the tree, block, surfaces, block surface. We're going to split this by patch here. Click on that, and it'll split it up by all the flat surfaces that we've got here. And it's nice to keep your model kind of oriented from that, or from the previous view, just so you know kind of what each surface is mentally. I know that this is the inlet because that's the way the car was pointing before I entered this. I'm going to go ahead, change that part name to inlet, click create, and you see it kind of disappears. Boom, car is facing this way, so we do know that's the inlet. We can set this one to the outlet. That's going to be the, we know that as well. It's the way the car's going away from. Create, that'll disappear. And then this final one, we're gonna create the floor. Yep, that's the floor. It's bottom of the sim. There's a car right there. And yeah. And these last three I'm not gonna touch. They're all grouped together originally, and they're all going to end up having the same surface properties when you go through and create the sim. And so it's a little easier just to leave them all together so you don't have to go change those properties 3 times. Yeah, so I'm just going to leave them like that, and they'll all still be together, as you can see in the sim there. And I'm just going to change this to walls, because this is the walls here, and rename it. I'm going to go through and rename actually a lot of this stuff here. It's not supremely necessary, but it does make the sim a little bit easier to understand once we've got a lot more components, different aspects in play here. So I just call that the tunnel. That's the name I always pick. And I'm going to rename this. You can see this body here. Body 2 is rear wing. And this is, the simplified car that I've gotten here right now. I'm going to rename this to rear wing just so I know what it is later on. And because we're gonna want to measure specific stuff on here and not all of this body, so that's just good to know. Okay, so once we've got our tunnel created, we've got all the surfaces set up properly, we've got our body in there properly, we're gonna want to go ahead and actually create a region. What this region does is it simply defines the area that Star is going to run its computations through. So we're going to go ahead and create that now. You want to click on either one of these bodies or parts, it doesn't really matter. Right click on that and go down to assign parts to regions. And this step may look a little different depending on what kind of sim that we're running. If we've got a lot of parts in there, we may do something a little different with our regions. But for these simple sims with 1 or 2 components that we want to test and then the tunnel, just go ahead and I add both of these to the same region. And then another important thing is to change this middle setting here, change it from create a boundary for each part to create a boundary for each part surface. And that's because, as we saw earlier, you split up all those part surfaces. We want to be able to assign individual characteristics to each of those. and yeah, we don't want to have, you know, characteristics for just the entire part. And then I just renamed this to air. Not super necessary, won't impact the sim at all if you do that or not. But you know, it might be nice. I like knowing what my region is. My region is air in this case, so yeah, go ahead and do that. Click apply here. You can see some stuff changing in the background, but it won't close, and then we can just close it ourselves. We can go check here under the regions portion of the tree and close some of this stuff because we won't need it anymore, but we've got our region air here. If we open this and check the boundaries, we've got our car body, our rear wing, our floor there, our inlet, our outlet, and our walls. You see the walls there. So we've got everything, and we can't fully define this region the way we want to without some of the other aspects of the sim being in place. But we can definitely, we can set a few things. We want to change the type of this here, the inlet. You can go on and just click it, and then down in properties here, we want to set that to velocity inlet, and that just allows us to specify a specific velocity for that inlet later on once we've got our physics continuum in place. And then for the outlet, we can also change this to pressure outlet, and that just allows, you know, whatever changes in pressure and airflow are caused by this body, it'll all just flow out nice and smooth. So those are the two things that we can change in the region right now. And then the next step that we're going to take is to create some continua. So the first continuum we're going to make is the mesh continuum. And what the mesh is, you know, as you will learn in your aerospace courses, for a lot of these fluid analysis, the way you do it is with a control surface and a control volume. And the mesh kind of breaks the entire your big region, you know, that box, and your parts here, your bodies. It'll break that into millions of small control surfaces and control volumes through which it'll do its computations. And there's a couple things that we want to do before creating that mesh continuum, just to make sure that we've got we're able to see it, we're able to visualize it, that if there's any issues with it, we'll be able to spot those issues, so that we don't have problems later down the line. So the first thing that we're going to do is we're going to make a derived part. This will also be useful for visualizing our solution, but we want to go to this derived parts bit of the tree here, right click it, go to new part, and create a section, and we're going to create a plane. You see it, you know, it takes the middle of that body and automatically creates a plane with it. This is not the direction we wanted in. We want our plane to look like that, splitting our body down the middle. And this will be very useful for the solution. We can actually see the airflow across the body on this plane. But it'll also help us visualize the volume mesh, those control volumes that we're going to create here. So we're going to go ahead. Once we've got this and it looks good, it's right down the middle like that. And go ahead and click create. And close. It's kind of difficult to see, but there's that, you know, nice tan line that represents that plane we just created. And so next we're actually going to create a new scene. So on the scenes bit of the tree here, we're going to click new scene. Right click on that, go to new scene. We're going to create a mesh scene, and this is going to show us our mesh. And I like to just hide these walls here. You can click on them in the image over here, right click, hide, just so we can see the model and we can see the meshes on this model. This is the most important bit of this process. And we're going to go ahead back to our derived parts here in the tree, and we are going to drag this on, and that'll add it to the scene. And so when we pull up a mesh, when we display a mesh here, it'll come up on that plane, and that's really good for visualizing the volume mesh, because you can't really see that unless you've got something within that volume that it'll show up on. And so now that we've got all our visualization stuff set up properly, we're actually going to want to go ahead and create that mesh continuum. So to do that, we're going to go to the continuous spot on the tree here, right click, go to new, create mesh continuum. And so now we've got it created. Not a whole lot of useful information in it right now, so we're going to add that. We're going to go to models here first, right click on that, and select our meshing models. And then this is just, how star is going to go about breaking up the surfaces and the volume. You're specifying that with these models. So we're gonna use surface remesher. Sometimes we use surface wrapper. It's kind of in my opinion, it's a bit of a troubleshooting tool. If you've got weird holes or something, or your parts aren't quite connected properly, in the CAD model, the mesh will, or the wrapper will kind of, it'll wrap it, same way you would wrap a package or something, I don't know. And it'll fill those holes for you to create a body that Star can actually do computations on. One of the main issues though is it may fill holes that you actually wanted. So for example, on our multi-element wings, it'll often connect two of those elements, and we really don't want that. That ruins our airflow. So we generally don't use this unless we've got an issue. We think it might help, but yeah, it kind of ups the computational intensity quite a bit. So if you don't have to use it, you shouldn't. I wouldn't recommend it. And then for volume mesh here, we're going to go ahead and select trimmer is the option that we're going to use. There's a couple different options there, and you can play around with them if you want. We've used polyhedral mesh in the past. It creates really complex polyhedral shapes for your volume. But obviously, yeah, those are a little more computationally intense to create, as well as for Star to run the solution through. The trimmer it creates squares, which is really nice. It's really fast to run, really fast to create that mesh, and it runs much quicker, and we're able to actually, we're still able to get pretty high level of accuracy with that, as long as you're specifying the right dimensions for your squares. And the other thing we're going to add here is a prism layer mesher. What this does is it actually creates a really fine rectangular mesh close to your surfaces, which is important. We want to get a nice simulation of the boundary layer on all our wings, on all our bodies, and that allows us to do that. So we definitely want to have the prism layer mesher in there for that fact. So I'm going to go ahead and close this. Now once we've got our models selected, we can go in and choose reference values for those. And this will tend to be, a little bit ambiguous. You can set these to whatever you like. Obviously, if you're going with smaller sizes, you're going to get a more accurate sim, but smaller surfaces, smaller squares, it's going to take longer to find the solution there. But yeah, I've got values that I like to use. I've got values that I know work with this simulation in particular. So I'm going to go ahead and input those and kind of just explain why I've chosen the ones that I have. So for base size here, we're just going to set it to 0.1. I tend to use that across a lot of our sims. I think it's a good size based on a model that's within a few meters long. It seems to work pretty well. And we're going to scroll down here. Maximum cell size. I'm going to set this to 500%, and you see relative to the base. So it's 500% of the base. The maximum cell size is going to be 0.5 meters on each side of the square. And that'll just create some bigger cells later farther away from the body, which makes it compute a little bit faster, which can be nice. Maximum core to prism ratio. This doesn't do much. Even when I set the value that I'm gonna set, I just enable that. and set that maximum ratio there to 5. That's what it is automatically. You can play around with that. It you know, makes smaller square cells right at the end of that prism layer. So yeah, you can get a little more accurate simulation really close to the body. Number of prism layers here. I'm gonna set this to 10. We use that. It's a pretty common number that we use across all of our simulations, and that's just, you know, you're gonna get 10 rows or 10 rows of squares or rectangles coming up off all of your surfaces, and I'll show you what that looks like once we run the volume mesh. And then we got prism layer stretching here. I don't change that. 1.5 seems to work pretty good. Prism layer thickness, I'm going to change this just to 10%. You make that smaller, you're going to get a, you know, tighter, more refined prism layer. And considering that this vehicle is moving relatively slowly, we don't have huge boundary layers. So that seems to work well. Seems to get the whole boundary layer. All the surface stuff I don't really tend to change. This, you know, if you've got issues, this can help you get a smoother mesh around, you know, your curved surfaces around like the wings and stuff here. But this sim will run fine without, the mesh will be created without issues there. And so we're going to go ahead. Last thing a few things we're going to change here are the surface size, and this relates specifically to the surface mesh. I like to set this to 0.25% of that base size that we set, 0.1. That's pretty small, you know. 10 to the negative 4th meters is your scale there. But if you've got the computational ability to handle that, you get really nice refined mesh around all these kind of round areas here, which is very good for computation, very good for simulating what we're going to see in the real world. So I like to try to keep that as small as possible, obviously within reason. If you set it super small, it's going to take a long time to compute. And then for the target size, I just leave that exactly the same. You get nice big surfaces on flatter areas where it doesn't matter quite as much. And then template growth here, this is specific to the trimmer, I think. But I'm going to set this to very slow. What that does is it just changes the rate at which the squares increase in size as you move away from a surface. I can show you what that looks like once we've run this, but yeah, and, you know, if you set that to slow, you're going to get more smaller squares near the surface or near the bodies, which helps increase the accuracy of the sim. But yeah, you can play with that kind of thing. You know, if you set it to fast, you're going to get lots of big squares and it'll run really fast, but it may not be quite as accurate as what you're looking for. So now that we've got this all set, we can actually go ahead and run the surface mesh, run the volume mesh as well. Yeah, to do that, you're just gonna want to go up to the top here, click on this white flag. It's initialize meshing. Just make sure you don't have any issues in meshing. And then we're going to go ahead and click on this symbol here with the triangles, and that'll start running the surface mesh. So we can see here, I just ran the surface mesh. It didn't show it because it takes a little bit of time. If we go down and look at the output here, this beautiful white box at the bottom, you see surface remesher has been completed. CPU time took 228 seconds. Yeah, so a couple minutes there, relatively quick. But yeah, now we can actually go ahead and change our mesh scene here to actually see this remesh surface that we've created. So we can go down, click on mesh scene here. If we open it, go to displayers, mesh 1, scroll down to the bottom. If we see remesh surface here, should take a second to change that view, but there you go. So now we've actually got, this is the surfaces that we're going to use to compute our final solution on. You look, we've got these little triangles. See, they get really fine right at like the leading edge of the airfoils here, where we've got a lot of curvature. You know, they're a little wider on these flat surfaces here, a little wider on the flat surfaces of our body of interest here. But yeah, you can see that, you know, tend to kind of look at the airfoils. You know, this is where issues come up. You might get choppy trailing edges here or something. You see, kind of get some weird stuff going on at the top there, but it doesn't look like we've got any shape issues. So this mesh should be all good to run. We like that. I'm actually going to save. I probably should have saved this sim a little bit earlier, but yeah, I'm at this point I'm pretty confident that I can get through this without issue. But yeah, you definitely want to, Star doesn't save automatically. You know, you want to be saving as often as possible, as often as you remember, just in case, you know, if you have issues here and there, you don't have to restart the sim completely. And there are definitely a number of places where issues can arise in this process. I'm just going to call this RW 8.13, that's the wing that we're running. Demo. Boom. Yeah, I'm overwriting an earlier version of this, but yeah, just make sure you've got your sim saved throughout the process, so if anything does go wrong, you don't have to, you know, go back and start from scratch. So now that we actually see we've got our surface mesh visualized here, the next step is to create the volume mesh. One thing I forgot to do earlier, it doesn't really matter for the surface mesh because it only runs on a single core or a single thread of your computer. But for the volume mesh, you definitely want to go click on the mesh here, or, you know, click on this, and you go down to the properties box here, and you want to enable parallel meshing, and that'll just, you know, that'll make sure that the Star is leveraging all the cores or threads that you have assigned to creating the mesh for maximum efficiency. And that maximum efficiency is pretty important because some of these bigger sims can take a long time to run and a long time to generate these meshes. So now that we've got that set up, we're just going to go up to the top right by where we click to generate the surface mesh. We're actually just going to click the box next to that and generate the volume mesh. So I'm going to go. Yep. And it's starting its thing. This will take a minute, so I'm going to cut here. Okay, so I just went ahead and ran the volume mesh. It should be all finished now. As you can see again in the output, volume meshing pipeline completed. This took 594 seconds, so just about 10 minutes there. This is a pretty big volume mesh, especially for something relatively simple. But yeah, they do tend to take a little time. If you've got a lot of cores here, like I do, that helps. But yeah, so now that that's been completed, I can show you the volume mesh, kind of visually demonstrate some of the features I was discussing earlier. To do that, we're going to go again to scenes, mesh scene 1 here, displayers and mesh 1. We want to set this to volume mesh. Set the representation here down at the bottom to volume mesh. And it'll take a moment to update. There. So you can actually see you've got kind of the projection of all these little squares on the surfaces here. And then if you zoom out, yep, you've got the a 2D representation of all those squares in the actual volume of the region here of the box that we created initially in the on that plane that we created. And if we zoom in, we can see here we can see the prism layer that I was talking about. You've got these little rectangles get really fine as you get closer to the surface, so you get a really nice boundary layer flow there. And you can see that here. It's most important on the airfoils. Make sure you've got nice, good sized prism layers there, and then you can also see kind of the size. All right, star is not the best for moving around and not the greatest controls there. But yeah, you can see these. You can see that growth rate that I set earlier, that very slow growth rate. You've got really small squares, especially around kind of the tighter points of geometry on the wings. And they get bigger and bigger as you move farther out, and they do that at a relatively slow rate. So you've got really fine mesh in here, fine mesh on this wing, and it expands out. It gets pretty big. So like back here, this is pretty big. This is a maximum size that those squares will get, and they'll run much quicker, which helps. You want this sim to be fast. Especially something simple like this. We don't want to invest 9 hours of compute time to run this, so having a simpler mesh back here can help with that. So now that we've actually got our mesh and we don't see any issues with it, looks all good. We can go through kind of the final setup process for this sim. So the first thing you'll see that once the volume mesh has finished properly, has been completed, you'll actually see this physics continuum appear here in the continua area, or continua point on the tree. And this is really important. This is where you're going to set a lot of, or all your your models for the actual airflow through your region. We're going to set speed and stuff in this. So what we're going to want to do, we're going to want to right click on that and click select models. And then we're just going to start moving through these and picking models that we want to use. So we're going to go with steady flow here. Gas, we're looking at air. Segregated flow. Equation of state, we're going to use constant density. And then we're going to use turbulent flow. And then the K-epsilon turbulence model. And I'll be honest, I don't 100% know what all of these things are. These are just kind of general physics models that we use on a lot of our sims, on pretty much all of our sims. They seem to work. I'm pretty sure we're getting decently close numbers there. But yeah, so those are the models that we're gonna use for this sim. We're gonna use for computation. Then we're gonna want to go down to initial conditions and change some of the stuff here. This is where you're gonna a lot of this stuff, this says 0 pascals per pressure. This will actually pull that standard atmosphere 100,000 101,325 pascals. Sorry, it'll pull that from here where you've got reference values, so you've got reference pressure there. So you don't need to change that. Turbulent intensity, some of this stuff is just constants for or numbers for the more complex equations that are being calculated through the simulation. And then the other initial condition we want to set here is velocity. And we're going to set that to -40 in this sim. And this is actually not necessary to set this. The sim will run fine without an initial velocity. But it speeds up the time it takes to converge, because you're going to start with the air moving in the right direction from the beginning, whereas if you don't have that, it'll slowly get there through iterations. But yeah, we're going to set that to positive 40, not negative 40. That'd be a big problem. But yeah, as you can see, we want flow to move from this. The inlet here is red, outlet is orange. We want it to move from the inlet to the outlet at the speed that we want to use, in this case 40 miles an hour. You can set that to whatever you want. You can also specify the units here, so you just type in miles per hour, meters per second, kilometers per hour. Most of our speeds are in miles per hour. Most of the analysis we do on speed is in miles per hour, so I just like to use that. But yeah, we want it to move in this direction, and that's, as you can see, based on the coordinates specified here, that's the positive x direction. So yeah, that's really the one thing that we want to change there. As long as we've got our model set, physics continuum is good to go. And now that we have that, we can go back and we can actually finish our region that we started originally, but we didn't have all the values. So now you can see we've actually got drop-down menus on all of these parts, and by default, like, you can look at this. There's mesh conditions, physics conditions, and then physics values. And by default, this is just a rough, unmoving surface. So you can see, oh, yeah, no slip. So air is not going to be slipping along that surface without friction. It's gonna have a boundary layer. Some of this stuff, you know, this is we actually, like this, we use for wheels. You can set a rotation rate. You know, this rear wing, we don't want it to rotate. So we're going to leave that. This one we're going to leave untouched. And we're going to actually go and change some of the values for the box. This is where we're going to want to specify certain stuff for each plane. And from that, yeah, that's how we're gonna finish out our sim here. So first up in the line is the tunnel floor. And this, what we're trying to simulate here with this is actually the road moving under the vehicle. And to do that, we can actually go in to physics conditions, and we can change this tangential velocity specification here. And we can change this to vector. And what that'll do is it'll make the velocity of that plane, you know, whatever vector we're going to specify here, and we go down to physics values, relative velocity, and we want that to be moving at the same speed as the air, because, you know, if the car was moving along a road, it would be moving at the same speed as the air. So MPH there. So now we've got essentially the road beneath it moving at 40 miles an hour, just like the air above it. So the next thing that we're going to do is we're going to set the velocity inlet. And this is where you actually set your airspeed for the whole sim. So we don't need to change anything in the physics or mesh conditions. But we do want to go down and change that velocity magnitude and change it to 40 miles per hour so that we get 40 miles per hour for every iteration coming out of that plane. We don't really need to change anything for the outlet here. That works, you know, does its thing naturally the way it's set up. And then for wall, this is where we're going to want to change, like I showed earlier, we're going to want to go in and change this shear stress here in the physics conditions. We're going to change this specification to slip. And then that essentially just means that those walls have no friction. You know, they're mostly to define the region. If we didn't need them, we wouldn't have them. So we want them to have as little effect on the simulation as possible, so we set them to no slip. Or we set them to have no friction, so they don't cause issues there. So now, with your region set up, this sim is actually ready to run. You could run this and get a solution. That solution won't be particularly valuable in that case, because you don't have any way of visualizing it or pulling data from it. So we're going to go through a few tools that I like to use, tools that we use in a lot of our analysis to get meaningful data from this simulation or any simulation you'll do in the future. So first thing we're going to do is we're going to create another scene. We're going to create a vector scene here. And this will, as you can see, it automatically has, you know, a little measurement bar down here for velocity of the flow. And we're actually going to add that plane section that we made originally. We're going to drag that in and click add to vector 1. doesn't show up really right now. If we go down to vector 1, so actually I moved over to scene here, scene/plot, different window, the simulation. If you click on vector 1, and down in the properties here, you want to change this to line integral convolution. The difference between these two, this is basically, it'll just show vector lines, and then this you get like a nice pretty color map. It's a little easier to look at and understand what's happening. But you can see there, we've got our plane in, we've got the silhouette of the body, and then this will show velocity vectors normal to that plane, or tangent to that plane, sorry, within the sim as we run it. And I like to have this set up beforehand. You know, it doesn't really matter. You can make any scene you want with, you know, streamlines or planes like this after you've run the sim. But this is nice to see. This will compute every single iteration you do, and then you can see if there's any like weird flow issues that arise. And you can stop the sim if that's a big problem, or if that's, you know, a problem with the setup, and fix it, or you can realize you can see what the issues are with the wing that you've created in real time, which is great. So once we've got that, we've got a way to kind of visualize our solution as it goes. The other thing that we're going to do is we're going to measure the downforce and drag on our body, our specific body of interest. In this case, I want to know the downforce and the drag on that rear wing. And so to do that, I'm going to go back into the simulation here up at the top, and I'm going to create a report. So right click on that, new report. It shows up here. Yes, force. So I want a new report of the force for downforce or drag. And yeah, to do this, we're going to go in and change a couple of the options here in properties. For downforce, you want that, you know, that's a force in the negative y direction here. So we're just going to go change this direction vector to 0, -1, 0. So that's measuring in the right direction. Pressure and shear, we're going to leave that's the same. Leave the reference pressure, that's the pressure that it's pulling from the simulation. And then we want to go into parts. And you can actually do this. You can either select the rear wing in the region or the parts. It doesn't really matter. I'm just going to select the part here. Yeah, so now this report is going to purely just report the force in the negative y direction on that rear wing. So yeah, click OK here. I'm actually going to rename it too, just so we know it's downforce. So right click, rename downforce. Done. Awesome. And then we're going to make another one for drag. So drag will be, in this case, in the way that I've got this sim set up, it'll be in the positive x direction. I actually didn't need to change that. Nice. So yeah, drag is that force pulling opposite to the direction of motion of the car. So yeah, positive x direction in this case. You know, leave this stuff the same. And we're going to go in, we're going to select the rear wing body. Yeah, so that's all set. That'll measure the positive x force on that rear wing. And I'm also going to rename this one to drag. Okay, so we got our two forces that we want to look at. Obviously, there's other stuff that we can measure. You can add other reports too. One that I always like to add is, see if we can find it here. Yes. Solver, elapsed time, this kind of stuff. Total CPU solver time, or total elapsed time, there we go. So that'll tell you how long the sim has been running. Can be nice to know at certain times. Also, you know, if you're getting super long iterations, you know, that'll report that. You can standardize it across sims, know what's fast and what's slow. So I like to have that in there. Not super necessary, but again, just good to have. And then once you've got all this stuff created, you're going to go up, right click on this, right click on each of these. We'll do this one by one. And you're going to want to create a monitor and plot from the report. So there you go. See, now we've got our plot here. It's got nothing on it because we don't have a solution yet. But yeah, once we run the simulation, run the solution, this will get populated with all the data points with the downforce for each iteration. And then we've also got, we can go here, see we've got a monitor for downforce right there. What this will actually do is it'll pop up in the output here. It'll pop up with the downforce for each iteration, and you can see that and see how it changes, so that's nice to know. Then we're going to do the same thing for drag, create monitor and plot from report. There we go. So now we've got our drag monitor plot. Alright. We've also got our drag monitor here in the under the monitors tab. So now we can see all that information in real time as the sim runs. And then also I'm going to create a monitor. I'm just going to create a monitor for my solver time. Obviously the graph of this is just going to be a line or linear because it takes, each iteration takes about the same time, so it's not super important to see that graph, but it is just nice to know how long this has been going. So now I've got that monitor in there. And for this sim specifically, this is really all that we're interested in finding out. These are all the kind of important values that we want to see as the sim is running, and all the important numbers that we want to get from the solution. So this is actually good to go. To run this, we're just going to go up here and click Initialize Solution. It's a green flag in the top bar here. Takes a minute sometimes to get all the all the data for the sim in line, so it's good to go, but hopefully we won't have any issues. Yeah, okay, there you go. Yeah, so it takes a minute to update, takes a minute to initialize, but as you can see here, one of the prime indicators that it's done besides the actual output in your monitor bar over here is that now we've actually got some vector lines in our vector field here. And this is just applying that initial condition of 40 miles per hour. I'm actually going to go in and I'm going to change this velocity unit here really quick. We can do that in vector scene just like we've done before. Yes, color bar, no. Vector field, yes. Units, we can change this to miles per hour. So yeah, you can see we've applied that 40 mile per hour condition, initial condition, to the entire region. Now that's represented on our plane. And it looks like we've got no issues initializing that solution. So one thing I'm going to do right now is I'm actually going to save this. It shouldn't take too long. Sometimes these large sims do take a while to save. I guess it is going to take a little while. But yeah, I'm going to save this and actually close it and then reopen it with more cores or more processes so that I'm leveraging my multi-threaded CPU so I can get this to run just a little bit faster. So yeah, closed now. Got nothing. Load. We're actually going to load this. I'm going to go ahead and load it on 30 processes. I've got 32 threads, but just in case I want to use this computer for homework while this runs, I've got a little bit of headroom there, just in case. Yeah, well, it's gonna take a minute to open, but here, yeah. Find the sim that I just created. open it just like you would have previously, just like we did originally. And it'll take just as long as it did originally. But yeah, so now we've got our simulation. You know, we've still got everything that we had originally, because I saved it last time, so I should have, but that's okay. But yeah, now we've got it. Actually, I can show you this here. This is my compute processes, and you can see now I've actually got 30 different executables open for star, so that'll be faster in the long run than having, you know, just 16 open like we did before. And yeah, I'm gonna go through, I'm gonna open all my scenes again, or open my vector scene really just so I can see that see that flow change in real time as the sim goes. And then I'm gonna also open my plots again here when I'm done, just so I can check that. Yep, so plots. We're gonna go ahead and open the downforce one, drag one, and go back to vector scene. So yeah, this actually is all ready to go. To run this, we're just gonna go up to the top, click this picture of a dude running, and let it go. So what just actually opened there is the residuals plot. Again, I'll be honest, I don't 100% know what all these do. But once we get a few iterations here, I can kind of explain the numbers that I look for, the numbers, or the lines that I watch for. You see you've got a little key in the corner here. I know that the TDR, that the turquoise line, is the kind of error in the sim, the level. You know, if that skyrockets, your sim is no longer converging, and you've got a problem there. You might want to end that and fix something, or you know, figure out what's going on. You know, this other stuff. You know, generally speaking, you want all these numbers to kind of converge to zero. You know, move towards zero. They'll never get there, but you know, that's a sign of a good sim. Yeah. And you guys see we've got our first iteration down here. Took 4.4 seconds to run that. We've got a number for drag, number for downforce. And these are not supremely useful at the moment because the sim is nowhere near converged. Takes quite a few more iterations than 2 to do that. But yeah, we've got some numbers here. We've got some stuff going on. And now you can see these graphs, all these lines coming in. We're actually going to switch over here and check out our, yeah. So this is the vector scene. Again, it's kind of messed up right now. You know, this will happen. Your first few iterations will be a little messy. Usually takes maybe 100 to get to a sim that doesn't have any issues, or you know, doesn't have any weirdness going on. And we usually run these for 1,000 to 5,000 iterations, maybe, depending on how important the given sim is. That tends to be a good number. I mean, 1,000 is the number that Star has default for the number of iterations that it'll run, but seems to be a pretty good number for getting a nice, well-converged simulation. As you can see, this is, our maximum velocity is here starting to come down. We're starting to get pretty, not great airflow over the wings yet, but it's getting better. If we go back over to the residuals tab here, hasn't quite come down yet, but you can see, we peaked at 1 here. It's going to start, all these graphs are going to start moving towards 0 in a minute. Yeah. Downforce and drag don't super matter at this point, because what you're looking at just isn't supremely accurate. But yeah, I'm gonna let this run for a little bit. Hopefully it'll converge, and I'll come back and show you what it looks like when it's finished, and some other stuff that we can do for analysis after it's done that can be useful. Okay, so I let this sim run for a few hours here. We actually go down and see it's been 28,000 seconds, so I guess 6-7 hours since I last was recording, and we've got a pretty well converged sim here. So you can see this is the kind of finished vector plot that we created. Now that we've got an actually well calculated solution here, it doesn't look quite as messy. So you can see we've got the wake propagating back all the way through here, and we're just tall enough that the height of the box doesn't really affect that. If we can zoom in, we can see flow around the wings. We've got high speed airflow here on the bottom, especially with that leading edge. We can look for kind of potential issues. We've got some separation on this foil here. Same there, kind of. But yeah, that's kind of how I would use this specific plot to analyze the wing. We can definitely make some changes here to improve efficiency, some stuff there, move these foils around. But yeah, this is what this setup will look like when we're initially finished here. We can go through. We've got our downforce monitor plot here. I just left this open the whole time. You can see it kind of steadied out here right around 390-ish newtons of downforce, 394. But yeah, nice and smooth, so we can at least have some confidence in this number. Same with the drag plot here, steadied out right around 130 newtons of drag. So it's pretty efficient wing, to be honest. It's a pretty good number there, especially for the downforce. It's doing a lot better than last year's rear wing. And then we can see these are our residual plots. So this is probably not the best converged sim. We would like to see numbers, especially for this TDR, much closer to 10 to the negative 5. If you actually look down here, you can see it in the monitor readout. We're at 2.6 times 10 to the negative 4. So this could probably be better converged, more accurate. We could kind of increase the average size of those mesh points, or decrease the average size of those mesh points, create a much finer mesh and bring that down, or create a bigger box, that kind of thing, so we can get a little more accuracy. Things I would look for when creating my next sim here. But this is converged-ish. We don't have huge issues, huge spikes or anything, so this is generally pretty good if you see this. And so actually, depending on what you're looking for, we've got our drag numbers, we've got our downforce numbers, we've got a decent look here at flow over the airfoils, not necessarily flow over the entire rear wing. There's other stuff that we definitely want to look at, and we can look at vortices and that kind of thing. But yeah, this is actually pretty well finished. This may be all you need for certain sims. When we're just testing a number of disparate designs in our initial process, that's maybe all you need to look at to know if a design is worth pursuing. But there are definitely some ways that we can further examine the wing, and I can go through some of those right now. So one thing I always like to check, especially as I get further into the design process, and we're working, with optimizing end plates or optimizing, different aspects of the wing, I like to check the vortices. A good way to do this is with a plane, just like we did previously, except this time it's going to be oriented it's going to be a YZ plane in this case, so kind of normal to the plane that we've already created, normal to the direction the car is moving. To do that, we're going to go back to the geometry scene. I just opened that right here. Again, we're going to go to derived parts, new part, right click on that, new part, and plane section. And this one doesn't actually snap to the body, and that's because we've got the block in there. But we can move this around, so we can actually, should be able to just drag this. There we go, yep. So yeah, we can just drag it right to the end of that wing there, get a good look at the vortices. We can call it 2.5. Maybe 3? No. 2.6. Yeah, so that's right at the end of the wing. I don't know, I think that just gives a pretty decent look at the vortices that we're getting. Just go ahead and set all these to a more consistent value. That's not necessary, but I think it looks nicer. So yeah, we can just go ahead and create that just like we did before. As you can see, this one actually shows up colored in tan, kind of, and that's just because the volume mesh is there, so it's computing that area within the volume mesh. And then to add it to this section, we can just drag, drop, click add to vector 1, and then there, we can get a really good look at some of the vortices coming off of this wing, and then the end plate as well. So you can see there's some high speed flow right there at the top of that end plate. You get kind of the same thing on the inside of the bottom. And then you can also see this these vortices propagate out. And clearly there's not enough space within the block for them to really hit their full size. You can see they're kind of running up against the walls here, so that could be part of the reason why that this sim did not quite converge as well as we might have wanted. But yeah, that's a good analysis tool. I like to use that one a lot. Another cool thing you can actually do, and I can show this on either plane here. We can go into vector 1. We can actually hide this plane. You can hide either of these planes if you just want to look at one or the other. Just right click on it and hide. But something cool that you can do, it can be useful in either direction, to kind of see the differences across the wing, is to animate this. And when you do that, you're gonna see either if you're doing it on this plane here that splits the body in half like this, you'll end up seeing how the flow is different across the span of the wing, or the wings that you're looking at. And if you do it on the other plane, you're just gonna see it, those vortices as they move backwards from the car. And to do that, you just go down here and click on the animation, and click discrete sweep. Actually, no, we won't continuous sweep for this, sorry. Yeah, and so then we can just set the time that we want it to move through. So, I don't know, 20 seconds. And then the start and end value. And this will just be the relative to the plane. So, we know that rear wing is about 1 meter wide. It's nice and centered, so we can move the plane from negative 0.5 to 5, or 0.5, and then we'll end up, moving through the entire region of the wing here. Yeah, so once you've got that set up, it's pretty simple just to go up here and click play. I chose here, I chose to pre-compute the steps, which means it'll just, compute each plane before running the animation. But yeah, here we can see the that plane moving through all the different positions between y equals negative 0.5 and y equals 0.5. And you can actually see the flow over that airfoil in all these different positions. And this can be just useful, especially for the rear wing and front wing as well, just because, when they're directly behind or in front of the car, they get different flow, whereas when they're more free stream on the sides, you can see that well represented here. But this is another useful tool just for checking out the flow on the wing, in a given direction without having to create a whole bunch of different planes. We can go ahead and show this for each. Sorry. Uh-oh. There we go. Okay. So now, yeah, we've got this plane as well. We got this one moving a long way. Yeah, so we got a different animation for that. And that's just moving through the whole region there. But you can see those vortices as they propagate through that plane. There they start to come off the car. Yeah. One useful tool that I definitely like here. Okay, the final analysis tool I'm going to go over here is how to create streamlines. These are pretty valuable. They show 3D flow. That can be useful in a lot of ways, especially for analyzing 3D bodies here. The planes show 2D stuff, which can be useful. They're pretty simple, but when it comes to these three-dimensional bodies, that's definitely, we want to take a look at how that flow is working in 3D. And there's a number of ways you can go about setting this up. I'm going to show you a way that I really like. It's a little bit more complex than some of the potential other options, but it's a really nice, clean look at the vehicle. And I'll show that here. So to actually make streamlines, you're going to have to create a part. To derive them, or that they'll flow from, or assign a part that they'll flow from. And you can do this, with parts already created. You can do it with the inlet person, for example. But one thing I like to do is actually go in and create a new plane to derive these streamlines from. And we're going to use this constrained plane option here. What this does is it just creates a plane that is not quite, or that you set to not be the full size of the box. You can set it just to be the front of the vehicle. So we can go in and set this, negative 0.35. Get it right on the nose there. Super nice. You don't have unnecessary streamlines out front. And then what we can do is go up here and click Modify Contour. And then we can go kind of just look at the front view. Throw some points in here. And get a nice box around our car. It's not the most precise way of creating something, but we don't really need the precision. We're just trying to create a plane that's a little bit smaller, than the entire area, so that we don't have unnecessary streamline. If you want to see the entire region, streamlines moving through the entire region, you can definitely set that up. Just as simple as this. Derive those streamlines from the inlet or something, but this is definitely a cleaner look, and you can kind of follow the streamlines better. So once we got that set, we can click Create here, Close, and you can see there we've got a plane that's a little bit smaller. It just covers that area in front of the car. And so the next step from here is we're going to want to go to Derive Parts again, click New Part, and create this streamline. And then once you're in here, hopefully your input parts, that should be your region, air, and then you want to go down here and click Seed Parts. Go to Derived Parts, and then click on that Constrained Plane section. And I can show you what this is in a sec, but I just want to create this. Boom, close. And yeah, there you go. We see we've got some streamlines around the vehicle. We can see some of that 3D flow very well. You can see how these vortices come off here. You can see the air moving through the wing. You can see cool stuff like this where it actually takes a dip down on the end plates. And you've got relatively simple, it's not super cluttered here. Pretty easy to analyze. And if you actually want to, add more streamlines, you want to make this even more precise look at what's happening, we can go in, right click on that streamline again, hit edit part in current scene, and then we can actually change these numbers. So if you increase them, that'll increase the resolution, increase the number of streamlines. So say we bump it to 10, click apply, and all of a sudden, man, we got a lot more streamlines. We can look a lot closer here to what's going on. You now all of a sudden have streamlines going through these slots in the wing. And you've got streamlines of air moving up here through our spoilers on top of these wings. So there you can see we've actually got a really tight vortex right at the top of the end plate. The more streamlines you add here, the more precision you can kind of get. But the harder it is to pick certain things out. And once you've created this, what you can do is go down, create a new scene, create a vector scene here just like we did before. Nice and simple. And you can actually just drag and drop the streamline onto that vector scene, add to vector 1. And you can see it'll already fill that in with velocities, which is really nice. You can see where that faster flow is. If we go in here and change some stuff, as you can see, we've actually got vector arrows on there. This is a little cluttered. It's kind of hard to see what's going on. So if we just go change that to line interval convolution here instead of glyph, you can see some streamlines. You can't actually see the body here, which is not supremely useful. Obviously, we can't really tell what's going on if we don't know where the body is. So I'm just going to change a couple things here. One, I'm going to go down. Change this to miles per hour. There we go. So it matches the speed that we picked initially. And then the other thing is I'm going to add that body in. And to do that, we're going to go to Outline here. And you see in the top of the properties, we want to go ahead and click, you see Surface here. There's a checkbox next to it. Click Surface. And then there you go. We've got all our surfaces in there. We can go ahead and hide this outer surface. You can hide other surfaces that you may not necessarily care about right now. And then now we can see these streamlines going around our body, with nice velocity indicators, so we know how fast the air is moving. So you can see we've got some really quick moving air on this vortex that we're getting off this top biplane wing. But yeah, this is a great way to go in and analyze little components of your wing and see what's going on there. Just little ways to tweak and increase the performance. Definitely this is a useful tool for that. But yeah, that's kind of all the tools I use for analysis in my design process. Yeah, that's all the steps I take to create a relatively simple star simulation. That's when I'm testing new wing designs, this is what I do. So hope you all learned something.